let's continue with the same topic, potential field, and now I'm gonna speak more on hardware rather than simulation. Just because too many people ask me after my sessions on potential field, all that is okay. I have a robot. Just tell me, how does that robot move with potential field? Just tell me that. So, of course, we've done a lot of work moving real robots with potential field over here, and that's exactly what I'm gonna say. Now, I'll start off with the one which is most intuitive, and in the most intuitive way, you have a camera which you mount at your ceiling and it looks down, and this is your arena, and the obstacles are clearly seen by the camera, and you take a robot and the camera looks at this red color, a normal color filter, and it's able to find out the XY coordinates of this robot and detect what are the obstacles. The goal is usually a bright flag, so that's a goal. Again, color detection can help. So attraction towards the goal can be easily computed. For this robot, not costing more than 1500, 2000, 2500. A camera, similar cost, cheap system. Now, usually universities have high ceilings, so you can actually keep in arena and looking down. But when we did that over here, our university has a very expensive system that's called as central air conditioning, and therefore the ceiling is false and small, so we had it oblique. Now the picture that it takes will be like this, and all the people who use mobile phone as a scanner would know. Now a lot of memes are made because of this technology, this homographic conversion. That can convert this into this. So finally you have a nice rectangular image, and because you have a nice rectangular image, you get in exactly the same maps. Attraction to goal can be easily computed. So there are two types of forces. Attraction to the goal can be absolutely easily computed. I'll take the conic as an example. Q is known, G is known. So all the terms are known. The problem is, so remember last time also I took a shortcut. I said that how do you calculate is what I'll answer right at the end. Now is the time when I unfortunately have to tell you how do you calculate dq comma o. And now I cannot escape. Now I'm talking practical. One way is to do it over each and every pixel, but that's going to take a long time. Remember, all this calculation leads to one unit move of the robot, and then you have to calculate all of them again. So doing it over each and every pixel is not suggestive. Here is where I say that my F repulsion is equal to max over O F repulsion. That means for any point in the scenario, I only have to consider the nearest obstacle, and I only have to consider the nearest obstacle. And that will be dq comma o, and only the nearest obstacle, because of this max modeling, only the nearest one will apply the repulsion force. Now the problem is, how do I get the dq comma o from the nearest obstacle as well? So my entire problem of calculating obstacle repulsion force from all the obstacle is reduced to calculating the repulsion from the nearest obstacle. Now I'll have a fact that this map is static. It's a toy problem. You get some obstacles, the map is static. A ceiling camera is looking at it, the map is static. Nothing changes in that map. And because nothing changes in that map, what I can do is I can pre-calculate all repulsion forces. And remember, this Q is basically a XY. So approximately this is 1 upon d cube, q comma o. Now, if I need to pre-calculate this, what I can do is I can just, okay, and that is, of course, the max over all O. So what I can do is I can calculate d of xy in this map, which is equal to, I need to maximize this, that I need to minimize this. So for every point, what is the nearest obstacle? Now, that's a problem that we have already seen into AI. So what was AI? There's a source, and what is the smallest distance from any point towards the source? That's how graph search is defined as. From any point, what's the closest distance to the source? From any point, what's the smallest distance from the source? For any point, what's the smallest distance to the source? That's exactly the same problem, except for I say my source is all obstacle boundaries. And therefore, I have a Dijkstra's type algorithm for a discrete grid all these points are at a distance of 1 from the obstacle boundary. These points are at a distance of 2 from the obstacle boundary. These are at a distance of 3 from the obstacle boundary, and so on. So I'd say distance of a point xy at a time t is nothing but minimum of distance between xy and neighbors, minimum at time t minus 1, the distance of any point x dash y dash from the neighbors plus the physical distance between xy and x dash y dash, where x dash y dash is a neighborhood function. And like AI, in AI we saw 2 neighborhood function. The first was this, 4 neighbors, 1, 2, 3, 4, and the other one was 8 neighbors, 1, 2, 3, 4, 5, 6, 7, 8. So what happens is that this is xy, this is x dash y dash, any one of the neighbors. So you say how much can I go to, I mean how much distance to the neighbors, whatever has been calculated so far, and from the neighbors if I go to xy, what additional distance do I get, and that's what the distance. And of course it's recursion, so d of 0 x of y is equal to infinity if xy is not an obstacle, and 0 if xy is an obstacle. and this only holds good for non-obstacle. So eventually it's just two ways you can think about it. The first is like any standard image processing filter, just apply this filter till convergence happens. The other way is it's a special Dijkstra's algorithm where you start over with all these points as neighbors of obstacles annotated 1 and use this neighborhood function as a normal Dijkstra's algorithm. We've done a lot of practice over it, so nothing to speak about. And then what happens is that I ultimately had to calculate the repulsion force at any xy. So I applied this xy. Now I also need the direction. How do you go to the direction? So from 2, and so how do I get the direction? Same way as you get the parent. So you find out which parent, which xy led to the smallest distance. Here this led to the smallest distance, so direction will be here. Here this led to the smallest distance, so direction will be here. The only problem that now you need to consider is because there's a discretization over here, there's a discretization in the angle as well. So earlier angles could be continuous and now angles can only be at one of these certain angles. Do this calculation offline. Calculate and store these parents offline for the angle. Then when the robot moves in real time, attraction force, you know the formula, you know Q, you know goal, just apply the direct formula, no assumption, nothing. Repulsion force, you know the distance to the closest obstacle, you know the parent, so you know the direction to the closest obstacle, so apply a force in the inverted direction, and you get your repulsion forces. This algorithm is known as the Bush-Fire algorithm. And the name is derived by, it's actually a very bad example. So you say that whatever you see as white are bushes, and those bushes behind which lots of lovely things happen. Those same bushes where, I mean, it's a form of life. And the obstacles are not bushes, they are rocks. So you put a fire across all the rocks, you put a fire across all the obstacles at exactly the same time. And then you simulate the fire going around. And then at every point you note down when did fire reach this place, that's the distance value. So what really happens is something like over here. So that's an example of bush fire. So the ones that you see directly as blacks are the actual obstacle, and this is the spread of fire. This is the spread of fire. So what you do is blackness is the distance from the grayness is the distance from the obstacle. So that's why you see these as white, far away from the obstacle. So you look at the grayness value, 1 upon grayness is the distance, and then take a gradient of this image, and the gradient of this image tells you which is the direction of the force. So that's the output of a Bush-Fire algorithm for 2 maps, and the whiteness is the magnitude of the force, inverse of that, and the gradient of this Bush-Fire image is the direction of the repulsion force, and practically you have got this thing. So that's the experiment that I was referring to. We had 2 cameras, we stitched their image. You do image stitching using apps these days. So that's the overhead image. That's called as an orthographic projection, of course. And then you use a Bush-Fire algorithm, and to get it, the thing which is noted down over here is what's called as a virtual proximity sensing. So you place a virtual proximity sensor. Now the reason I don't tell you that is because the virtual proximity sensor is like a LiDAR or a sonar. It sends an electromagnetic wave and that comes back, and because electromagnetic wave strikes and comes back, you note down the distance. If you have to simulate this algorithm, you need to know an algorithm called as ray tracing. That is, you are given the direction of a ray, you are given the geometries of all obstacles, and you need to find out at what distance will the ray strike the obstacle. Luckily, you don't need to write those algorithms. Those are pre-made at most of the libraries that we work with. So if you're using virtual proximity sensors, you need to know the ray tracing algorithm,